Okay, hello everyone. Welcome back to the Intercontinental Seminar series of Gravity and Cosmology. So today we are very happy to have Professor Yuting Huang to give us a presentation. Professor Yuting Huang, he got his PhD in 2009 from Stony Brook University, and after that he went to UCLA and also University of Michigan, and also the Institute of Advanced Study in Princeton as postdoc. And then in 2014, he was back to National Taiwan University, and now he is a professor in NTU. And in particular, Yuting is one of the leading experts in the calculations of gravitational S matrix. So today, he's going to talk about bootstrapping the gravitational S matrix. So please, Yuting, the stage is yours.
Okay, thank you very much, Dale, for the invitation and very nice introduction. It's very nice to have this opportunity to give this talk. I will basically talk about some recent fun that we've been having on this topic of doing bootstrapping, which is in particular the S-matrix bootstrap. And so this talk will be mostly more like a review, just give you a bird's eye view of what's been going on, what is the basic, what are the assumptions, and what are the results that are derived. Of course, since there's many activities, so I've basically just handpicked a few highlights to discuss. And so this is more probably a reflection of the vicinity of these work related to what I've been working on. But basically, in terms of the gravitational S matrix, I think that basically the questions that we are basically trying to answer is that we like to understand the space of consistent completions of gravity. So what do I mean by that? What do we mean by the space? Well, we are basically trying to formulate this following something that has been done with much success, which is the space of conformal field theories, which has been going on for a while and has been very successful. And basically, the attitude that one takes is that that one would like to implement or to utilize the consistency of physical observables, and using this to give precise model-independent statements. And so, just to a quick review of what the conformal field theory people have been doing. So, what this falls under what is called the conformal bootstrap, and for example, one starts with the physical observable. One can, in the CFT, one generally talks about the 4-point function of correlators. If we're specific to 2-dimension CFT, you can think about the partition function on a torus. And then one, of course, imposes a series of consistency conditions, the conformal for the CFT for the 4-point correlator. One can use conformal invariance, crossing symmetry, and unitarity. And then the 4-point function will have to satisfy something like a crossing equation, which just says that the OP expansion of the 4 operators in one channel has to be equal to the OP expansion of the 4 operators in another channel. On the CFT side, it's just a statement about defining your partition function on the torus, where this torus has a torus moduli, and this change in moduli parameter actually corresponds to the same torus. So when the partition function is written in 2 different ways, they actually have to give you the same observable. So using this, people have been successfully obtaining, for example, giving us the maximal gap of the system, extrapolating what are the density of the states, and a particular bounds on OPE coefficient. So like these informations that come from this lines of reasoning are model independent because they're just using fundamental principles. And since any theory that we might be interested in must satisfy these principles, we get model independent statements that are universal. Now, of course, as we are interested in quantum gravity, actually, this whole CFT bootstrap is already answering these questions to a certain extent through, of course, ADS CFT. Since the 4-point through ADS CFT, the 4-point correlator can be understood as a bulk gravitational theory, where the degrees of freedom in the gravitational theory interacts, and therefore by ADS CFT, finding the space of consistent CFT essentially gives you information about the consistent theories of gravity in ADS. Of course, we're not in ADS space, and we're more interested in flat space or approximately flat space, and therefore we're trying to mimic what has been done in conformal field theories. And so in gravity, the most natural, if you assume that you have an asymptotic flat region, the most natural observable that you might want to look at is the S matrix. So this will be the main focus of this talk today. And so basically we will be considering the scattering of 2-to-2 scattering of particles, so P1, P2 being the two particles. So we are the 2-to-2 scattering of P1, P2 to P3, P4. And this is given by an amplitude, which depends on two parameters in general. The parameter S, which is related to your center of mass energy, and the parameter T, which is related to this scattering angle here. Of course, in the usual quantum field theory, you also have the scattering amplitude. So of course, it becomes even more interesting that the same observable appear in the usual quantum field theory and in the theory of gravity. So we can ask what are, and as you will see in for certain questions, we can actually pose the question of what is actually the gravitational effect? How does gravity changes what you usually see in quantum field theories? Now, the one important reason that that looking at this observable is interesting is because a large region of this observable is actually already well known. I mean, so again, this is supposed to be a function of two variables: the center of mass energy and the scattering angle. Just to make the discussion more easier, we can do a Fourier transform and transform from momentum space T to impact parameter space, so roughly speaking is related to 1 over b, and then consider the amplitude as a function of two axes, the center of mass axis and the impact parameter axis. Then this function here in different regimes of this on this plane is actually controlled by different physics. So for example, at low energy but large impact parameter here, this is the usual weak gravity region where we basically just have the Born approximation. You have the one graviton exchange, or you essentially just has gravitational effects to linear order in G Newton. And then when we go into this region, which is we start to go from large impact parameter to what is called the iconal region, which is S going to large, but T over S is small. Then this amplitude is dominated by what is known as the iconal scattering, which is basically a sum of infinite number of graviton exchanges, but just ladder exchanges. And this, of course, gives you the usual case where the S matrix in this case is given by just a phase where we have what is called the iconal phase. And this is also computable. And so basically the statement is that for this function, even before going anywhere, we already know what the answer should look like in this large region here. Okay. And so essentially what one is trying to do is one is try to leverage the analyticity of this amplitude, and where a large part of this amplitude is already fully determined. And we're trying to use analyticity to continue to relate informations that we might be interested from here or here to what we can observe at low energy or finite impact parameters. So this is the idea that we want to do. And so before going into how do we actually do it, but let's just stop and think about let's say we can actually do this, then what are the questions that you might envision that you can ask about low energy physics if we have the tool to do what I just said. So so we can pose the following questions, which of course by posing I mean that we can actually answer them. So for example, what is the space of consistent gravitational EFT? So for example, What does this mean? So what this means that for a gravitational EFT, let's write in the Lagrangian here, we expect that since at low energy we see Einstein-Hilbert, so we expect that when we have high energy effects or quantum gravity effects should come in as more and more higher derivative operators involving more powers of Riemann tensors or derivative of Riemann tensors. And for example, D and R to 4. And for each of these Riemann tensors, we have, for each of these operators, we have these coefficients. And so in some sense, this gives us the coordinates of what we mean by theory space, right? So the coordinates are these coefficients here. So what are the allowed regions of these coefficients? Of course, from a pure low energy theorist point of view, these coefficients is just parameterizing our blindness to what has actually happened to in the UV. So these parameters and principles are just arbitrary from a low energy perspective. Of course, as we will show that if we actually implement certain assumption about the UV, for example, unitarity, some general principle assumptions, actually we will find that these parameters are actually non-trivially bounded. What is actually more interesting, as you will see, that these actually turns out that we can actually provide constraints on this space that actually impose constraints on the low energy spectrum. So what do we mean? So for example, this can be, as I will demonstrate, that this can be, we can give you bounds on the number of species that you can have at low energy related to your cutoff, and we can also tell you non-trivial information about the representation of the degrees of freedom that you have in your gravitational theory, transforming under some global symmetry. So the spectrum is going to be constrained. Of course, since many people have been studying the different versions or different string theoretical model, so it'll be very interesting to ask. So since now that we have a parameter for our theory space, how much does string theory or string theory inspired answer actually span these space? So where exactly is string theory in this space? And actually, if we actually add more additional assumptions than just general assumptions, for example, we can assume that we are interested in tree-level completions, meaning that that the quantum gravity is completed while gravity is still weakly coupled, which means that the completion scale is below M Planck. That means that the completion will be tree-level like, and therefore you are going to have a bunch of resonances. What can we say about these resonances? And finally, of course, we can add additional assumption that at certain the energy that one might be interested in, one has supersymmetry, then what kind of additional information can we get? So these are the type of questions that I will demonstrate that we actually have answer for. Okay, good. So now let's get into business. So how did we do this? Or what are the fundamental principles that we've utilized? So essentially, it just comes in 4 different pieces. We have the boundedness, the analyticity, the unitarity, and crossing. So I'll go through what each of these statement means. So boundedness is just a statement that this function MST as a function of S, let's consider as a function of S. So this is the complex S plane. This function is bounded by S squared as S goes to infinity. So as this contour goes to infinity, this MST over S squared vanishes as S goes to infinity. Okay, and there's various ways to see that this is actually true. Well, I mean, intuitively, this is just a reflection of causality, because as we know that S is related to energy, and when we do the decomposition, energy goes as exponential IET. And of course, then if you continue energy on the complex plane, the fact that you have causality tells you that this function has to decay sufficient fast on the upper complex plane. Then through a Short's reflection principle, it will also be bounded in the lower complex plane. So the causality will tell you that this is bounded. The precise boundedness by S squared, we have to use a little bit more information. In fact, for gravity, this is very non-trivial. But as it turns out, since, as I mentioned, we know how gravity behaves in certain region. In particular, we know in the amplitude, the behavior of the amplitude in this region. This region is just governed by classical GR. And we have the Econo approximation here. So we actually know this information, and we can use this to prove that for gravity, the amplitude will be bounded by s squared. So this is boundedness. Analyticity is a statement that amplitude is actually analytic on this complex plane. So the non-analytic part can only happen on the real axis, which corresponds to different physical processes, either for particle production or that we have non-trivial running of loops, which creates physical branch cuts. And so, for example, so that means that all the non-analyticity is living on the real axis. We can split this non-analyticity into two regions. One is the UV part, which we don't know what's going on. And one is the IR part, which in principle, we have an effective field theory description, which may or may depend on the approximation or the answer that you're asking, may or may not include loops. But basically, this part is computable, and this part is unknown. So we're basically trying to relate the computable part to the unknown part and try to get constraint for the parameters here. Unitarity reflects in this picture as the statement that since the only non-analyticity is here, so that means that the information that you're going to pick up is going to be the discontinuity across this real axis. But we already know from the optical theory that discontinuity is going to relate to the imaginary part of your partial waves. And from unitarity, we know that the imaginary part has to be definite positive. So we know that the contribution from these discontinuities is always going to be some positive coefficient multiplied by some orthogonal function. In 4 dimensions, this would just be a Legendre polynomial. And finally, for crossing, that just means that the discontinuity and this part, which corresponds to the S-channel discontinuity, and the discontinuity on this part, which is a negative S, which is reflect the U-channel discontinuity, are actually the same discontinuity. So this is just crossing the statement of crossing symmetry. So this is the fundamental principle we're going to use, and we're going to try to get so I'll demonstrate to you that we're going to get a lot of mileage from these 4 assumptions. So how do we leverage these? So this falls under the what is called the dispersion relation. And so the dispersion relation just used, so first it starts out with our boundedness statement. Since I know that my amplitude is bounded by s squared as s goes to infinity, that means that this integral ds, integrating over this contour at infinity, is 0. Okay, so s minus s, so there's s1, s2, s3. So these s1, s2, s3 is just some parameter that you can put in here. You can choose it to be 0. You can choose it to be other Mandelstam variables, just depending on the convenience of your problem. But these are just some coefficient, some fixed points that you can choose depending on your problem. This is what usually people call subtraction points. So basically the point is that this integral, this part is really ds over sq as s goes to infinity. Since m over s squared is 0, vanishes sufficient fast at infinity. Therefore, this counter integration is 0. So this is 0. Okay. Now this counter, of course, can be broken into two pieces. You can view this counter as going this piece plus this piece. Okay. So since the outer contour is 0, that immediately tells you that this IR part here, and the discontinuity of your UV part are directly related. Here, this h of s is just I don't want to write this function here. So whatever that comes from the above, I just write h of s. And finally, then we use crossing to relate that the discontinuity of the U channel is related to the discontinuity of the S channel. To write this into to write the right-hand side is a single integral, which is just a discontinuity of the S channel. And finally, unitarity tells us that this is just the imaginary part of our partial wave times the polynomials. Okay. And so that means that this is positive in the sense that this continuity here is positively expanded on a set of orthogonal polynomials. And therefore, this allows us to relate what is happening in the IR to what is happening in the UV. And the only thing I'm using in the UV from now on is that this is positive. Good. So now I'm going to show you a few examples of what one can get. So in this talk, I will be focusing on two scenarios. So we will consider EFT of gravity or massless scalars coupled to gravity. Let's just use this simple. Of course, we can generalize this to massless vectors, massless fermions, whatever the situation you might be interested in. But let me just demonstrate using gravity and massless scalar. So again, we start out with this formula, where again we are integrating the IR amplitude. So in principle, this part is supposed to be computable in your effective field theory, and this is the unknown part. If we're considering the scattering of scalars, that means that at low energy in general, we're going to have this is the gravitational exchange between two scalars. So this just reflects this type of Feynman diagram. And then you have an infinite series of polynomials, which I label by GKQ. And these are just a reflection of operators that are like d4 to the d phi to the 4, or d square phi, for example, phi square, and so on and so forth. So these are just higher derivative operators of scalars. So this is the right-hand side. This is the left-hand side. On the right-hand side, the discontinuity is again just the imaginary part expanded by the Legendre polynomial, as I mentioned before. Now, if you want to, instead of considering the scattering of massless scalar, the scattering of graviton, then all that changes is just that your amplitude now also has a dependence on the polarization vector of your graviton polarization, and usually this just comes out as an overall factor that are carried in 4 dimension by these spinor helicity variables. In higher dimension, these just becomes a gauge invariant operators that are universal, that sits in the front. And we'll be essentially interested in these scalar functions that come behind it. And so, of course, we again have the pure Einstein gravity contribution here and an infinite expansion, the polynomial, which, of course, this is now related to operators of, for example, r to the 4, or d and r to the 4 operator. On the right-hand side, this continuity now is again the partial wave, but now instead of expanding on the Legendre polynomial, we're expanding on the Wigner D function in 4 dimension. In higher dimension, again, there are generalizations. And this is just reflecting the fact that now the thing that you're scattering actually have polarization direction. So this has non-trivial information that goes into this Wigner D function. Okay, so let me just show you an example of what the result will look like. So for example, just for massless scalar, this will be an example plot that one gets. Forget about this plot. So this plot here is just we first formulate a theory on a more symmetric version, and then we rotate it into the physical axis, which means that the physical axis means that we're rotating into an expansion in S and T. But in the end of the day, this is our the space of coupling for our Wilson coefficients, which are these G couplings here. And the non-trivial thing that I want to show you is just that statement that this is actually a bounded region. So as I mentioned, from a EFT point of view, you might think that anything goes. So these operators should take on any value. But in fact, if you actually implement the consistency that it can be completable to a UV physics, which is unitary, the resulting space you get is actually non-trivially finite. And in fact, even though this was first derived from semi-definite programming, which is a numerical programming that optimizes constraints, most of the time, these boundaries we can actually derive analytic results from a completely different analytic approach, which we understand this dispersion relation through a geometric language. So this is the space of coupling for 6 derivative and 4 scalars field, and 8 derivatives and 4 scalar field. Now, if we want to do gravity, for example, we can bound, as an example, d8 r to the 4 coefficient even though I just write d8 to the 4, of course, the Riemann tensor and the derivative have many different contraction of their vector indices. And so writing d8 to the 4 just really includes a class of different operators. And that's why when we plot it, it actually gives a 2-dimension plot. And once again, we see that the allowed region from unitarity shows that it's actually a finite region, which in the end is this region here. However, as many of you noticed right away, that if you show explicit theories, you can have the type 2b string, the heterotic string, or you can just have theories that emerge from integrating away massive vector or massive fermions. Then the known theory actually populates a very tiny sliver of the allowed region in this EFT, in this space of consistent EFTs coming from this dispersion relation. So the space is actually very large. Okay, this region is very large compared to the known theories. However, it turns out that, of course, this is just a 2-dimension slice. If you try to see this in 3 dimensions, which means that there's 2 directions, right? There's 2 different couplings I'm plotting here. So if I plot a third direction coupling, so now here I just draw the contour of the third coupling. So let me just enlarge this. This is something I can do with my iPad. So you notice that actually for most of these regions, the third coupling is actually very small, 10 to the minus 9, 10 to the minus 13. So actually, if you look at this from a 3-dimension point of view, this whole region actually looks like something that looks like a potato chip. So it's very thin, and just in some finite end area that it has a region where it actually has something that is that has some finite finite size, which is around this region here. So on this orange curve, you can see this goes into 10 to the minus 1. And so if you go even enlarge that region here, you can see that all the currently known theories sit right in the middle of this region. Okay, so this is a very interesting observation that we're still looking into. But this is very interesting because it looks like there's some kind of a statistical interpretation in that when we have this kind of larger region among the space that is carved out by these dispersion relation, all the known theories actually lives here. So it looks like it's more probable for the known theories to actually live here in this tiny sliver. So if I just plot this 3-dimension plot and just look for the optimal region, and that's actually exactly where the known theories are actually living in. So it'll be interesting to explore this kind of feature, which we actually already see in various different plots, but it'll be interesting to systematically explore this. Okay. Now, however, you'll notice that these are just EFT coefficients. These are just EFT coefficients that I have defined. That we have defined. Sorry, let me just go back a little bit here. We have defined here. So these are just polynomial expansions, but all of these plot actually you don't see G Newton here, and the reason is following. Which is very important. And the reason is that, remember that in IR, so for example, if we're just scattering masses scalars, this is the IR form of your amplitude. This is the irrelevant operator part, and this is the graviton exchange part. If we try to, so since this is defined as a polynomial expansion, that means you're essentially expanding near t equals 0. So if we consider going to t equals 0, then this form simplifies dramatically into this form. However, you notice that there's a 1 over t pole. Okay, this is precisely the graviton pole that reflects that gravity as a long-range force. But the fact that gravity is a long-range force immediately also tells you that anything that, if you want to use a dispersion relation on the left-hand side, which involves the G Newton here, the G Newton will carry something that is diverging as t equals 0. That means that on the right-hand side, if you try to equate this with some UV contributions, then this contribution will diverge or goes to infinity as t goes to 0 as well. Okay, So that means that if you want to capture G Newton, you somehow have to play around with this dispersion relation by keeping T actually, by having able to both keep T finite, but at the same time acknowledge that there's a non-trivial 1 over T, because that's telling you that this is gravity. And very nicely, in 2021, Simon Keren-Hoyt and his collaborators developed a way to circumvent this divergent property, which is basically saying that we have the dispersion relation that looks like this, that has a divergent piece here. Then all one does is to multiply this with the test function. Let me just multiply this with the left-hand side and the right-hand side with the test function, and then integrate t equals 0 to some cutoff scale, such that this 1 over t gets smoothed out. And how to smooth out this 1 over t, it basically goes into how do you design your smearing function. But once you do this, now we can derive bounds that relate to couplings with respect to G Newton, as demonstrated here. So this is roughly the coupling for the R to the 4 operator, and this is the coefficient for R cube operator square. So G3 is multiplying R cube, and G4 is multiplying R4. Okay, so now we can get non-trivial bounds that involve G Newton. Now, what is this useful? Well, for example, the very nice paper last year was a proof of the famous species bounds. So there has been a belief that there is actually a bound on the number of matter fields below the cutoff, or the quantum gravity cutoff, that is parametrically related to that takes this form. So we have the number of species n lambda times the cutoff cell lambda, of course, depends on dimension. It has to be smaller or equal to n Planck with order 1 numbers. Okay, so this is what is, so that means that your species cannot be too large. And now this can be directly proven just using the dispersion relation. Okay, so once again, we can consider, we consider the scattering of gravity. So for gravitational scattering, we're going to have the polarization contribution in front, and then we're going to have the scalar function. Now, of course, when we're considering the gravity 4-point amplitude, considering the gravity 4-point amplitude, we know at low energy there's going to be, of course, the pure gravity effects. But then, because if you're considering matter fields below the cutoff scale, that means that you're going to have matter loops. So these are matter. And these matter loops, because of equivalence principle, these matter loops will, of course, couple to the graviton. So these will have non-trivial contribution to the 4-point gravity amplitude at low energy. And we can compare the contribution of this part and the UV. And so this is basically the plot, and of course the 3 has to add up to 0. Okay, and so this is the plot of this coefficient here, and so this is impact parameter, of course. So adding up the Einstein-Hilbert part, the matter loop part, and the UV part, they have to add to 0. Okay, so so what this means is that the matter part, so this is the low energy contribution that is being plotted depending on the spin. And you'll notice that at low impact parameter, which is B low here, the low energy matter loops actually dominate, which means that the contribution from the UV cannot be too much here. But at higher energy, not high energy, but higher impact parameter, now the low energy loops actually gets heavily suppressed in the sum rule. Okay, and the remaining part has to be compensated by UV. Okay, But since this has to be always added up to 0, so this immediately, so that means that, for example, that means that if you have a certain distribution of different number of spin 2s, this is, yeah, different number of spin 2s, spin 0s, then when they add it up, they all, for each impact parameter, they all have to add up to 0, which immediately tells you, since at low energy that the matter loop is dominant and high energy they're suppressed. So in order to satisfy this, the matter loops at low energy cannot have too big a species, and so you can immediately derive bounds that take up this form. Okay, so this is a non-trivial example. Now I switch to how much time? Oh, okay, I already probably have only 40 minutes left. So now that we have these different kind of plots here, we have these regions that we've able to plot it out. So we can actually ask how much of this region is spanned by string theory type amplitude. And it turns out, so I'm just going to do a little bit quicker here. It turns out that just, for example, for the scattering of dilatons, this is the allowed region. But if you consider linear combinations of string theory type answer and then impose unitarity, it can actually span most part of this region. Okay, so and notice that here when we're doing this spanning, we're just doing these string theory type amplitudes, which actually only have poles. Okay, which means that even just assuming tree level completions, oftentimes the tree level completion already spans a large region of the allowed space, which will be important as I will show you soon. Okay, so let me just skip. This is just a few examples of how the space is being spanned. So since I've told you that in explicit demonstration that in many cases that just using a string theory tree level amplitudes we are allowed to span most of the space. Therefore, it makes sense to focus our answer. So what more can we say if we actually assume tree level completion in the bootstrap context? And it's pretty surprising that we can say a lot, and this was realized last year. So so what does it mean that tree level completion? So previously, if I go back to the original plot, that original diagram that I just draw, bear with me a little bit. So remember that we've said that the amplitude in general can have discontinuities and branch cuts along the real axis. So when we say tree level amplitude, that means that, and the IR, that means this that means that for the UV completion, sorry, let me just erase this. So for the UV completion, we're just going to, instead of branch cuts, we always have particle production poles. So that's what we mean by tree level completion. Okay, so this is what we're going to assume. And in fact, we don't even have to assume everything is tree level. Let's just assume the first state is a tree level. So we have the first, when the UV physics kicks in, it kicks in as an isolated particle. Let's just even assume that. It turns out you can say a lot of things with this. So it was proven last year, again, using these numerical bootstrap methods, that actually, if you consider a spectrum that looks like this, so we only know that when the UV states come in, it comes in as a stable particle. And then there's a gap here, which is parameterized by mu times m gap, where m gap is the mass of this first UV state coming in. Then numerically, they immediately showed that actually the spin of this first state here cannot exceed 2 for non-gravitational theory. If you have gravity, meaning that you have a non-trivial graviton pole, it was demonstrated that actually the first state cannot have spin exceeding more than 4. So there's only 3 choices for the first state: 4, 2, 0 for gravity, and for non-gravity theory, it can only be 2 and 0. Okay, and of course, and this is the plot that they should was the numerical thing that they showed that they showed us, And basically, this is the coupling of this massive higher spin state to the low energy state. They normalize with some EFT coupling. And you can see that depending on the spin, so on top here, this is the spin 2. The spin 2 is perfectly fine. The maximum value of spin 2 generically for different, this Kmax just means the number of constraint is stable with respect to the constraint. But immediately, once you go beyond spin 2, spin 4, spin 6, spin 8, it gets heavily suppressed. It already goes to 0 0.1, 0 0.01, and so forth. And in this paper, they extrapolate that when the number of constraint goes to infinity, this actually is forced to 0. And it's actually, so even though this is a numerical extrapolation, later on in this paper, the two of the authors actually analytically proven that this has to be true. Okay, so this is essentially proven analytically. Okay, so even just assuming that the first state is isolated as a stable particle, we immediately have a non-trivial information on its spin. For non-gravitational theories, it can only be spin 2, and for gravitational theory, it can only be up to spin 4. And in fact, if you try to maximize, if you try to consider theories that maximize this coupling, this coupling lambda j here, it turns out that these theories exactly live on the boundary of the plot that I just showed you before, just using numerical bootstrap. So these are really interesting interesting scenarios where these gap couplings are maximized. So far we've been talking about scalars with just single scalar scattering. And so for the next probably 5 to 6 minutes, I'd like to just go through very fast what you can say when the scalar actually now transform on a non-trivial irreducible representation of global symmetry. So what this means is, of course, that your scattering amplitude now carries indices that represents the E-rep of your scalar field. And of course, at low energy, this amplitude will have a gravitational piece. And since the graviton is a singlet, its E-rep is just exchanged at Kronecker deltas. Of course, we're going to have a non-trivial polynomial term, which reflects the EFT coefficient and contribution of the high energy states. And these coefficients can be either expanded on Kronecker delta basis for fundamental scalars or for trace basis for adjoint scalars. Now, if you introduce color, what is actually interesting is that when you do a partial wave expansion on the amplitude, now the amplitude has to be positive expanded. So this is the partial wave, the imaginary part of our partial wave. It has to be positive on two bases. One is the kinematic basis, which is the Legendre polynomial that we had before in 4 dimensions. And then we also have this color basis. The color basis is in terms of projectors. So it has to be positive in 2 different spaces. There's a graphical notation for what these projectors are. For example, for adjoint scalars, there's 6 possible different E-reps that can be exchanged under adjoints on the outside. This is just the n-tableau. You just have 2 adjoints, you multiply, you re-expand it, and see what kind of E-reps you can get. You can only get 6 of them. Okay, so we just run through the dispersion relation again, and we impose positivity. And this actually introduces some non-trivial constraint. So just to show you how powerful this is a very cute example of doing this. So let's just go back to string theory. Let's say we don't know anything about the fundamental of string theory, but just give you the string theory answer. So the string theory answer for the scattering of 4 gluons is given by this. So this is the field theory part, which is just the graviton exchange plus the gluon exchange, is multiplied by a string G function here, which is just gamma function. And of course, I just mentioned before that the residue that you have on these function has to be positively expanded on your polynomial. So we just directly, you can take Mathematica, evaluate this residue. And for example, this is the residue on level 1 for the 6 different E-reps. Remember, all of these things have to be positive. Look, we look at these two. So these are definite positive, but positive for generic n. N is the rank of your gauge group. But this is not manifestly positive. Okay, the fact that this has to be positive and this has to be positive immediately show you can run Mathematica. It immediately tell you that n cannot be greater than 35. Okay, so just by using this positivity, you see that there's a bound on the rank of the gauge group. Of course, this is implementing positivity on explicit amplitude. What we would like to do is to see what non-trivial constraints that you can get in a generic context. So let me just I think I don't have much time left. So let me see, how should I proceed this? Let me just let me just go through I just use 2 minutes to go through very quickly. So the dispersion relation generically looks like this. Again, you have the low energy part related to the high energy part. Now, the only thing new here is that the high energy part, you're going to have an S-channel projector representing color state exchanging in the S-channel, and a U-channel projector. Now, on both sides, they're written in the color space, they're written in projector, so we want to put it in the same basis. So we can change the S-channel projector into the T-channel projector, as well as the U-channel into the T-channel. So we have this, to put them into common basis, we have this very simple linear transformation matrix, okay? Now comes the interesting fact that so I'm rewriting things, and I'm just rewriting things into this T-channel basis, and so these are the matrices here. So the important thing is that if for these matrices you can find a vector such that when you dot it into it, it lies in this common null space, then if you dot this vector on both sides of the equation, what you get is that you get the equation that looks like this. Because it's in a null space, on the right-hand side is going to be 0. But on the left-hand side, because of the fact that this vector has 1 and the singlet entry on the left-hand side is going to leave behind the graviton pole. But this is singular. Even though there's a polynomial expansion here, but this singular and t equals 0, this can never be 0. So what does that mean? That means that the spectrum that you've chosen, because when you're choosing this vector, that corresponds to choosing a spectrum, is just inconsistent. Okay? So this immediately tells you that using this dispersion, it immediately rules out certain UV completions of gravitational theory, because it's gravitational because we're using the fact that this 1 over t here plus dot 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 cannot be 0 if there's a singularity here. And for example, just to show you, sorry, I've been putting too much details here. So for example, of the 6th representation, all these linear combinations, all these subset of combinations, so the 1 is a singlet, the 2 is the symmetric one, and 3 is another symmetric representation. The 5 is a joint, and the 6 is anti-symmetric representation. So for example, all of these 3 subsets of UV completions are just completely ruled out by our analysis. Okay, and in fact, for three representation complete, there's only one unique possible completion, which involves the singlet, the joint, and the anti-symmetric representation is the unique 3 irreducible representation. Of course, you can add more, but for if you only allow 3, then this is the only possible 3 irrep UV completion. So this is 54. Okay, so let me just finish. I'm just going to skip to conclusion. So basically, what I wanted to show you was that the S-matrix bootstrap program has provided a fruitful arena to pose sharp questions for quantum gravity, and questions which can be answered. Questions that fall into what are their implications for low energy physics in terms of, as we've seen, that they provide non-trivial bounds on the EFT coefficients of your low energy effective field theory. They impose bounds on the number of spectrum, the number of low energy particles that you can have, the number of species, and also, if you assume tree level completions, this imposes non-trivial constraints on the spin of your first gap state, as well as impose non-trivial constraint on the irreducible representation of these states under a certain global symmetry. And of course, this allows us to parameterize the space of consistent theories in terms of parameterizing the space using these EFT coefficients. And in particular, we can look at the volume of these space that are being carved out. And of course, there's much to remain to explore. Maybe if we have time to discuss in the Q&A session, then I'll just leave it like this. Okay, thank you very much.
Hey, thank you, Yuting. Very nice talk. Any questions from the audience?
Yes, Huang Yu.
The thing is, he was just clapping. So I actually have one a few questions. So first of all, can you go back to the plot where you show the amplitude as a functions of S and T, the energy and also the angle. It's a very beginning plot.
Okay, sorry. You mean this one?
Yeah. So the one after this
Oh, this
size.
one.
Yeah, this one. Yeah. So what do you mean by quantum limits there on the left-hand side?
Yeah, because yeah, I was really mostly using just the first quadrant for this plot. Yeah, actually, I'm not very sure what he meant by quantum limit. This was I used this from Steve Giddings' lecture.
Oh, okay.
Yeah, that's a good question.
Would that be due to some point where the S matrix cannot be computed? No, the amplitudes cannot be computed beyond that line.
So for example, this should corresponds to. I think that this should corresponds to. So this will correspond to energy, and energy is now becomes smaller than M Planck, and the impact parameter is smaller than 1 over M Planck.
Oh.
Yeah, I think that yeah, sorry, I'm not exactly sure.
And another question is about so in one of slides you show that the three dimensions of parameter space, the theory
Yeah.
space can be constrained. I mean, particular one of them can be constrained, but the other two remains. I mean, they are finite, but yeah, like this. So do you have any interpretation about the fact that one of the dimension is is constrained more tightly compared
Yes,
with the other two?
yes, yes. So why did this two dimensions so wide, and yes, so the reason is because actually so this is in some sense oops, okay, for some reason I cannot erase it. Yes, so there's a difference. So here this says we're taking ratios of so let me just write this. So when we write BKQ, K actually represents the number of derivative for this operator. So you notice that we're actually taking ratios of operators that are of same dimension for these two dimensions, for these two directions. These are operators that are the ratio of operators that are of same dimension. So for this is actually B40 over B00. So this is actually I think this is D8 r to the 4 normalized with respect to r to the 4. So these are actually operators of different dimension. And so it's usually this is this because we're normalizing the cutoff to be 1. So unless there's fine, so in other words, in some sense, these areas here actually corresponds to fine tuning, because you see that their ratio are very small. So any theory that lives in here has to be extremely fine tuned, because we're normalizing our cutoff to be order 1. So we're normalizing our cutoff to be 1. So naively, each of these coefficients should be order 1. So if you take ratios of these should be like roughly order 1 numbers. So if you were actually living inside here, this has to be extremely fine tuned.
So that basically constrains the order of derivatives that can appear in your effective field theory, right?
No, no. This is not about constraining the number of derivatives that you can. I mean, that just course. I mean, the number of derivatives just corresponds to how good you want to do your effective field theory to approximate the answer, right?
Yeah.
The better you go to higher derivative. No, I mean, I'm just saying that first of all, the difference between these two direction and the vertical direction coming outside of the plane here is that the horizontal direction are normalizations of operators that are of the same dimension, the same derivative order. The direction coming outside is I'm normalizing with respect to something that has a different derivative order.
Mm-hmm.
So this is first thing. Now, so that means that this operator and this operator, of course, in power and cutoff, this operator will have higher degree of cutoff divided by lambda to the power meaning divided to the lambda to a certain power compared to this operator. Now my lambda is set to 1 for this plot. Yes. So if you are actually if you are the extra 1 over lambda suppression is not showing up here, which is good. So if you have high suppression, if you have suppression that sits here, which are suppressed by these order, these have to be extremely fine-tuned. That is why all the physical theory is living here.
I see.
So what is interesting is that most of the region that this 3 dimension that even though when we're plotting it, we show that there's large region in principle, but actually most of them you can just rule it out by saying that they're too fine-tuned.
Mm-hmm.
So this is a statement that this theory space that we were already constraining to be very small, but actually you can even remove it if you actually add the information that you're not allowing fine-tuning. Or yeah. And actually the known theory is non-fine-tuned, and so that's why they live in this tiny sliver, because there's only a tiny sliver that allows you to be non-fine-tuned. Mm-hmm. So this kind of bootstrap have teeth. That's basically what this plot is saying.
Let's see. Any other questions?
Oops. Or there's something in the chat.
Xu Wen asks a question. So given theories clustering in the parameter space, where would QG loop quantum gravity be? Would it also be in this region if we know how to construct effective field theory of loop quantum gravity?
Yeah, if loop quantum gravity can compute, well, I mean, if it could, I mean, even give the EFT, yeah. But I mean, if it can compute an observable, then we can put the observable in here and see where it actually sits. But I guess that's one of the challenges of extracting. For example, so here for us to see where loop quantum gravity is, the loop quantum gravity has to give us the low energy 4 graviton amplitude. What is the 4 graviton amplitude? Once we have that, then we can know where it actually sits in here. Then we can put it as one of the dots here. So because we have explicit answer from these theories, and therefore we know where they actually sit.
Okay, so let me ask a follow-up question, because since she will mention another approach of quantum gravity. So I was also trying to compare this approach with, for example, symptotic safety approach where like people try to find again the rounding of different coupling coefficients in the effective field theory, and the people believe that in the UV limit there should exist some fixed points for those coefficients. So do you think these two approaches can be connected in some certain context, or yeah?
Yeah, that's an interesting question. So of course, like, indeed. So what this is saying. So what this is saying is that anything that is unitary in a UV will have to live inside here. That's basically what we're saying. We're saying anything that is unitary. So that means that, of course, if you have it, but we don't say whether or not the UV is a fixed point or the UV is a string theory. We just say the UV is unitary. And that's how it is. It has to, so it's a loop in some sense. Asymptotic safety has to live in here. Of course, the difference between asymptotic safety and string theory is that string theory has an explicit UV completion where where you can compute things in the UV and then you can extrapolate which point it actually sits in the IR. Whereas the asymptotic, because you don't know what the fixed point is,
Right.
and so I cannot follow like a RG flow that goes from the fixed one and flow to the IR and see where actually where actually land in the IR. So that's the challenge of trying to see where exactly are you sitting in this plot if you're doing asymptotic safety.
Mhm.
But
Thank you.
yeah, but the same is that asymptotic safety I mean, by construction lives in here.
Yeah, I see. Thank you. Any other questions? If not, maybe we can end the official section of the presentation. I just stop recording.
Okay, thank you very much. Thanks for the time.